Good afternoon, students. It is so good. It is so exciting. It is so thrilling to have you in my class this semester. Today, we're going to be talking about thermochemistry. So some fundamental ideas associated with thermochemistry. But just before we begin, I want to remind everyone, you are not alone. This is an academic community. Remember to get help when needed. Reach out to the university services if needed. Never give up. Never give up. Keep trying. We are here to help you be ethical, intelligent, and successful scientists. However, at the end of the day, you must be responsible, ethical, and hardworking. I just want to share a few inspirational words by the famous poet Douglas Malloch. The tree that never had to fight for sun and sky and air and light, but stood out in the open plain and always got its share of rain, never became a forest king, but lived and died a scrubby thing. The man who never had to toil to gain and farm his patch of soil, who never had to win his share of sun and sky and light and air, never became a manly man, but lived and died as he began. Good timber does not grow in ease. The stronger winds, the stronger the trees. The further the sky, the greater the lake. The more the storm, the more the strain. By sun and cold, by rain and snow, in tree and men, good timbers grow. So what we want to take away from that, or what you can take away from that, is that even in the midst of adversity, when you approach it actively and constructively, there can be an opportunity for growth and development. So hopefully in this class you were able to grow and develop, and you're able to thrive in this General Chemistry 1 class. So, I want to remind everyone, we're winding down the semester, so I want you to really buckle down, really go through the videos, really listen to the podcast, take detailed notes, and really do your best so that you can do well. Let me change the view of my screen, full screen mode. There we go. So I want to remind you that the goal of this class is to teach chemistry content in an engaging manner that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows. Understand the fundamental concept A. Practice problems relevant to the understanding of concept A. Learn more nuanced details about each concept, and then practice more complex problems that integrate the details and the fundamental understanding. So we are on thermochemical equations, Hess's law, bond enthalpies, and we'll talk a little bit about the Born-Haber cycle. So let's proceed. There we go. So I want to remind everyone that some key rules to understanding for the Born-Haber cycle is that bond breaking typically is endothermic. It requires the input of energy. Bond formation is exothermic. It results in the release of energy. The Born-Haber cycle involves the metal going from solid to gaseous, the halogen going from atoms to molecules, the ionization of the metal, then the ionization of gaseous chlorine, then the formation of the crystalline solid. So trends in lattice energy. As the ionic radii increase, when you move down the column, the ions cannot get as close to each other and therefore do not release as much energy when the lattice forms. Lattice energies become less exothermic with increasing ionic radius. These are just typical trends. And then lattice energies become more exothermic with increasing magnitude of ionic charge. So that's kind of what I want to talk about for the Born-Haber cycle. Now, bond enthalpies. Bond enthalpy is associated with bond energy. A bond's length is dependent on the type of the bond. The greater the bond order, the shorter, the stronger the bond. So the higher the bond order, the shorter and the stronger the bond. Okay, so bond energy is the energy required to break 1 mole of the bond in the gas phase. And bond enthalpy is the heat energy released or absorbed when bonds form or bonds break respectively. So, what we're talking about today is Thermochemistry. So, keeping these big ideas in mind, we want to talk about what is energy? Why should we care about energy? What is it? Energy is the capacity to do work or to cause change. Its SI unit can be joule or Newton meter. Potential energy is derived from an object's charge or a charge's position, or an object's general position. Kinetic energy is derived from the object's charge on objects. Kinetic energy is derived from the object's or a charge's motion, so it's derived from motion. Now, what is a system? A system is the object under observation. The surroundings are everything else outside the object under observation. So, a key thing to keep in mind when you talk about thermochemistry is energy transfer. It ties right into the first law of thermodynamics, in which you say that energy is never created or destroyed. It's only transferred from one form to another. Another way to put that is the energy of the universe is constant. That depends on how you define the system, but classically, the energy of the universe is constant. And we also say that for endothermic processes, these processes require the input of energy, and typically the reaction coordinate diagram has the products at a higher level relative to the reactants. Exothermic processes typically result in the release of energy. Typically, the reaction coordinate diagram has products at a lower energy level relative to the reactants. So what is enthalpy? Enthalpy is the heat of a reaction. For reactions of 1 mole, for reactions for 1 mole of a reagent at STP, there's a standard change in enthalpy that occurs, which can be used to predict a reaction stability. Now, also with Hess's law, for a stepwise process, the change in enthalpy is the sum of the enthalpy changes of the steps. So we're going to really focus in detail on Hess's law today. Hess's law is named after the Russian chemist and doctor Germain Hess. Hess helped to formulate the early principles of thermochemistry. His most famous paper, which was published in 1840, included his law on thermochemistry. Hess's law is due to the enthalpy being a state function, which allows us to calculate the overall change in enthalpy by simply summing up the changes for each step of the way until the product is formed. All steps have to proceed at the same temperature, and the equations for the individual steps must balance out. Hess's law is applicable to other state functions such as Gibbs free energy and entropy. The heat of any reaction, so enthalpy, change in enthalpy, or standard change in enthalpy of formation for a specific reaction is equal to the sum of the heats of a reaction for any set of reactions, which in sum are equivalent to the overall reaction. So, let's talk about Hess's law some more. Say, for example, we have the enthalpy of reaction. We have a reaction in which hydrogen gas, 1 mole of hydrogen gas, is reacting with 0.5 moles of diatomic oxygen gas, and that forms 1 mole of water. The change in enthalpy, or the standard change in enthalpy, is negative 572 kilojoules. And then the next reaction shows 2 moles of diatomic hydrogen gas plus 1 mole of diatomic oxygen gas reacting to form 2 moles of water in the gaseous form. And the standard change in enthalpy for that reaction is negative 1144 kilojoules. Now the sign of the reaction enthalpy changes when the process is reversed. The sign of the enthalpy reaction changes when the process is reversed. So if it's negative, it becomes positive. If it's positive, it becomes negative. In this instance, the reaction that we're going to flip, or we're going to use in reverse, has a negative enthalpy sign. So when we switch it, it becomes a positive enthalpy. Since enthalpy is a state function, it is path independent. Therefore, it does not matter what reaction one uses, in a sense, to obtain the final reaction. You have to use the reactions that give you the net flow of reactants to products. So inferentially, we can get the standard change in enthalpy from using Hess's law. So 1, if a reaction is multiplied by some factor, then the change in enthalpy of a reaction is also multiplied by the same factor. 2, if a chemical reaction is reversed, then the change in enthalpy of a reaction changes sign. 3, if a chemical equation can be expressed as the sum of a series of steps, the overall change in the enthalpy of a reaction is the sum of the steps. So all is saying, we account for changes in each step of the reaction as we use Hess's law. That's essentially what it's saying. So if we multiply a reaction by some factor, the change in enthalpy is multiplied by the same factor. If we reverse the flow, or if we change the direction of the reaction for this purpose, the change in enthalpy will change sign. Or we have to change the sign. And if the chemical equation can be expressed as a sum of a series of steps, the overall change in the enthalpy of a reaction is the sum of the steps. Okay? So just keep these in mind. Enthalpy of formation, which is associated with the release of the amount of heat energy associated with the formation of a product in standard state. Calculation of enthalpy of reaction, we'll discuss that later. Calorimetry, which is basically associated with the measurement of heat flow. Specific heat, molar heat capacity. So you have heat capacity, which is basically the amount of heat necessary, the amount of heat associated with changing the temperature by 1 degree Celsius. Specific heat is the amount of heat required to change 1 gram of a substance by 1 degree Celsius. Molar heat capacity is the amount of heat required to change 1 mole of a substance or raise the temperature, this is a better way to put it, or raise the temperature of 1 mole of a substance by 1 degree Celsius. So let's go through that again. Heat capacity, the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Specific heat, the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Molar heat capacity, the amount of heat required to raise 1 mole of a substance by 1 degree Celsius. Okay, so let's just go through a few questions. So say for example, we're calculating the kinetic energy in joules of an electron moving at 6.00 times 10 to the 6 meters per second. So that's the velocity. The mass of the electron is 9.11 times 10 to the minus 28 grams. It's close to it's 9.11 times 10 to the minus 28 grams. This is the problem, situation of the problem. So what is the first thing to do? We look at our given values. We're given the velocity of the electron, 6.00 times 10 to the 6 meters per second. We're given the mass of the electron, 9.11 times 10 to the minus 28 grams. So if we have the velocity, we have the mass. How do you approach this type of problem? We're looking for kinetic energy. So let's proceed to discuss. And I'm going to type out how we can go about solving this type of problem. So if we know that kinetic energy is 0.5 mass times velocity squared, velocity raised to the 2. So if we know that kinetic energy is half mv squared, and we're given mass, and we're given velocity, then the product, so kinetic energy is going to be equal to 0.5, the mass 6.00, 10 to the minus 20, 10 to the 6, positive 6, and then so we put those in brackets. This is a way to note this as you type it. Meters per second. And then we multiply that by 9.11 e to the minus 28 grams. What's that? Kinetic energy is going to be equal to 1.64. So when we multiply those, we actually have to raise the velocity is raised to the second power. So that's going to be another brackets there. Okay, brackets, sub parentheses. So 0.5 open bracket, 6.00 times 10 to the 6 meters per second, close bracket, raised to the 2, close bracket, times open bracket 9.11 e to the minus 28 grams, close bracket, and that's going to give you 1.64 times 10 to the minus 14. And kinetic energy, remember, energy is a scalar quantity. It has magnitude, and we characterize it, or we describe it using joule in this context for this problem. That's the unit of energy that we are describing. So, draw it back. We have given a problem. They asked us to calculate kinetic energy in joule. We were given the velocity of the electron in meters per second, so we have ISI units. 6.00 times 10 to the 6 meters per second. Now, a key thing to note here is joule is another way. Joule is going to be, let me write this down. Joule is going to be kilogram meter squared per second squared. Let's just hold on to that idea for a minute. Joule is going to be, another way, the units for that will be kilogram meter squared per second squared. So why is that important? The mass of the electron is given to us in grams. So if we were given the mass in grams, a key component to determining the solution of this problem would be the conversion of the mass in grams to kilograms. So that would just be multiplying it by 10 to the minus 3 or dividing it by 1,000. That's another way to say that, to account for the fact that it takes 1,000 grams to make 1 kilogram. So you could use dimensional analysis, and you could plug and chug, or you could just multiply it by 10 to the minus 3, understanding that the prefix kilo is referring to 1,000. Okay, so that's that. And let's proceed. Let's move forward. Let's talk about question number 2. So we were given again the kinetic energy in joules of an automobile weighing 2,135 pounds and traveling at 55 miles per hour. So how do we solve a problem like this? They also helped us out, and they gave us the information that says 1 mile is equal to 1.6093 kilometers, and 1 pound is equal to 453.59 grams. So if I was given a problem like this, I would write down what I'm given. I'm given those conversions, those equivalencies. So I'm given that 2,135 pounds is the mass of the automobile. The velocity is 55 miles per hour. So considering how one of the big players for this calculation is velocity, I'm going to convert miles per hour. I'm going to convert that to meters per second. That's the first thing I'm going to do. So what that would mean is 1 mile is 1.6093 kilometers. Another way to say that is 1 mile is 1.6093 times 10 to the 3 meters. Remember, kilo is 1,000, or you could just think of that prefix in your mind as 10 raised to some exponent. So 55 miles per hour times 1.6093 times 10 to the 3 meters divided by miles. So I'm talking to the dimensional analysis. Miles cancel. And then we also say that 1 hour, 60 minutes, 1 minute, 60 seconds. Cancel, 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 cancel. We work that out and we get our conversion to our conversion into meters per second. That's that first step done. So we have our velocity in meters per second. And then we take 1 pound and we look at our automobile is given in the mass of 2,135 pounds. So 2,135 pounds times 450. The thing we want in the units, this is a key idea or key observation to note as you do your dimensional analysis working. What you want, you keep that on top. Typically keep that in the numerator of the things you're working on when you do your dimensional analysis. Sometimes that can change, but that's just a quick tip. So 2,135 pounds times 453.59 grams, and that's pounds going to be in the denominator. And then we also convert that grams to kilograms. Yeah, because remember the unit of joule is kilogram meter squared per second squared. So we want to keep that in mind. That's the North Star for this kinetic energy problem, that unit. So we have it. We have our mass in kilograms. So remember the formula for kinetic energy is going to be 0.5 mv squared. So 0.5 times the mass, which we just solved for, times the velocity, which we just solved for, squared, that velocity squared, and that's going to give us the answer of B, 2.9 times 10 to the 5 joules. So let's keep going. Calculate the kinetic energy in joules of a 150 pound jogger. And they give us the mass in kilograms. 6.81 kilograms. And the person is traveling at 12.0 miles per hour or 5.36 meters per second. So we have our mass in kilograms, we have our velocity in meters per second, so we just square the velocity value, multiply it times the mass, and we multiply this whole thing by 0.5 or a half, and we get a kinetic energy value, which is going to be 978 joules. Let's keep going. We have a bullet, or to make this more euphemistic, we have an object. We have an object traveling at 300.0 meters per second. Kinetic energy in joules. Kinetic energy is going to be 0.5 mass. Kinetic energy is going to be 0.5 times the mass of the object times the velocity of the object squared. So 0.5 times the mass, which is going to be 80. However, we want to make sure that the mass is given in grams. So we convert that to kilograms by noting or remembering that kilograms, 1,000 grams is 1 kilogram. So 80, if I'm given a mass in grams, all I have to do is multiply it by 10 raised to the minus 3, and I get the mass in kilograms. So 80 times 10 raised to the minus 3 kilograms, and that's the mass in kilograms, times the velocity, 300 meters per second, squared, 0.5 times that, and that gives me the answer of 3.60 times 10 to the third joules. Let's go to the last one. We have a 23.2 gram object moving at a speed of 81.9 meters per second. So the same thing again, 23.2 times 10 to the minus 3 gives us the mass in kilograms, moving at a speed of 81.9 meters per second. So 23.2 times 10 to the minus 3 kilograms times 81.9 meters per second, and that velocity value is squared. All of that is now multiplied by 0.5, and we get a kinetic energy value of C, 77.8 joules. Let's draw it back again. So we have our 0.5, kinetic energy is going to be 0.5 times the mass, 23.2 times 10 to the minus 3 kilograms, times velocity, 81.9 meters per second squared, and that is our value of kinetic energy. And the value for that, the answer to that is C. So also, let's talk about calorimetry briefly. Calorimetry. So I'm going to do this approach again. So Chemistry DBTeX is a good resource for chemistry students. It has a lot of literature. There are a lot of good notes, good explanations, different academics explaining the chemistry concepts in ways that are really conducive for learning. It's, in my opinion, it's a typical example of differentiated instruction in which you have concepts being explained in different ways to reach different types of learners. That's a prime example of a lot of things, but one thing is clear: equity. It's a way to democratize chemistry education. It's a way to provide equity in education for chemistry content. It's very, very, very useful resource, and I highly recommend it. So let's just talk about calorimetry. And as we talk about it, I'm going to show you. Say, for example, I was approaching this literature for the first time. This is just an explanation of how I would approach it as your lecturer, as your professor for this semester. How would I approach this type of literature? Say, for example, I'm working a part-time job, going to university, and I want to incorporate reviewing calorimetry, whatever that is, to my day. I just came home, say, for example, I just came home from work. I have about an hour or 2 hours or so before I deal with my family responsibilities, before I deal with my work responsibilities, before I deal with wrapping up for the day. How do I incorporate those things? How do I do well and do life at the same time for this specific piece of literature? So what I would do if I had to do all of those other things and do calorimetry, I would take it from the standpoint of I would actively read it. And read it to the point where when I come back at it again for the second, third, and fourth time, I have exposed myself to the content in a good way, or in a way that is memorable and it can be associated with my current framework for chemistry. So after all of that, let's just go and do some annotations now. So it says the objective. Let's see what our objective is. The objective is to explain the technique of calorimetry. We know calorimetry is measurement of heat flow. To calculate, and also we want to calculate and interpret heat and related properties using typical calorimetry data. So let's just do our SQ survey question, read, review, recite. So let's survey the material. It says a calorimeter is a device used to measure the amount of heat involved in a chemical or physical process. So let's just say calorimeter is an analytical device used to measure the amount of heat. So we just put that inside for now, top there. That's a big idea. Okay, and also it goes on to give examples as to when an exothermic process occurs in solution in a calorimeter, the heat produced by the reaction is absorbed by a solution, which increases its temperature. And then it goes on to discuss some well-insulated calorimeters that all to keep in mind with surveying the material. Then we're going to do a detailed read. It goes on to discuss that scientists, I need to do the annotation for this. Scientists, that's a good one. Scientists use well-insulated calorimeters that all but prevent transfer of heat between the calorimeter and its environment. So there's no transfer between the system and the environment or system and surroundings. So in some instances, a calorimeter could be considered a closed system. This is just a sidebar, but let's continue reading. It says scientists use well-insulated calorimeters that all but prevent the transfer of heat between the calorimeter and its environment. So we have two things that we could associate with what we are familiar with. We know things can be used to measure things, so calorimeter. And then we know that it's well insulated, so it's like a closed system. So let's just keep those big ideas in mind, and let's move on to the next page. Close that. Okay. Okay. Now this goes into some equations and stuff like that associated with heat transfer within the or heat release, heat flow within the calorimeter. We're not going to discuss that today. Just wanted to expose you as to how to read this material. But before we conclude, I want to remind everyone, or let everyone know, that since the first one was constructed in 1899, we're specifically talking about a bomb calorimeter. First one constructed in 1899, 35 calorimeters have been built to measure the heat produced by a living person. Calorimeters are useful, so just think about calorimeters. Calorie is the energy. So calorie is the energy unit used to quantify the amount of energy derived from the metabolism of foods. Remember, energy is released in the process of metabolism, or when metabolism occurs. Classic examples with respiration. But a way to really associate this concept of calorimetry is think of the calorie. Calorie is the unit of energy associated with the heat energy. Let's slow down. Calorimetry, think of the calorie. The calorie is the energy unit used to quantify the amount of energy derived from the metabolism of foods. So that's one way to associate that. Calorimetry, calorie. And then we also can associate with the fact that metry, calor, heat, metry, measurement of heat flow. So we break the word down into syllables. We also get a definition from that. And then when we think of a calorimetry, we can think of a well-insulated coffee cup, closed system. And because it's a well-insulated system, we can analyze the heat energy associated with a substance or with a particular piece of material in that closed system or in that well-insulated system, and we can measure the heat associated with that material because it's a well-insulated closed system. Okay, and then so just quick definitions. Bomb calorimeter is a device designed to measure the energy change for processes. Keep in mind we're surveying the material. This isn't the real read. It's just a quick survey. Device, a bomb calorimeter designed to measure the energy change for processes occurring under constant volume, commonly used for reactions involving solid and gaseous reactants or products. So let's read that again. A bomb calorimeter is a device designed to measure the energy change for processes occurring under conditions of constant volume, commonly used for reactions involving solid and gaseous reactants or products. Let's think about the calorimeter as a device used to measure the amount of heat absorbed or released in a chemical or physical process. Calorimetry, process of measuring the amount of heat involved in a chemical or physical process. Nutritional calories, we talk about the big C now. Big C, unit used for quantifying energy provided by digestion of foods, defined as 1,000 little c calorie, or 1 kilocal. So big C is 1 kilocal. Surroundings, all matter other than the system being studied, and system, portion of matter undergoing a chemical or physical change being studied. So guys, I know this was a quick read, quick survey, but the way I would go about this is I would survey the material if I had a little bit of time and do probably a detailed read of the first page and the second page, and try and really absorb what it's saying, annotate as much as possible, raise some questions, and then when I go to lecture, as if I was a student, in a general chemistry 1 class. When I go to lecture, hopefully I'm reading ahead of time or ahead of the lecture. So when I go to lecture, I have another opportunity to reinforce the material and then practice problems. So this is one way to approach it. There are other ways to approach it. You can watch videos, you can listen to podcasts, you can do all three: lecture, videos, and podcasts. And I hope you are doing well. I hope you are staying safe. Hope you're enjoying the class. I want to remind everyone, you are not alone. So keep it up. Keep up the good work. This is an academic community. We're here to support you. Keep it going. You're doing well. So that is where we are going to stop for today.